All right, hello everyone. So it's time to kick off a new unit here. We're going to be talking about aromatic substitution reactions. So talking a lot about those aromatic benzene derivatives that we learned about last chapter and the types of reactions that we can actually do to them. They will be substitution reactions, okay? First, we're going to talk about the most common one, which is the electrophilic aromatic substitution reactions. So let's just remind ourselves real quick. One of the first functional groups we talked about last semester were alkenes. And alkenes will react with electrophiles for an addition product, right? So I'll have my double bond is actually broken and something's been added to both of those carbons. But we learned about our aromatic compounds like benzene. They don't like to undergo such reactions because benzene is just so super duper stable that in doing so, if it were to undergo this reaction, it would go from being an aromatic compound to a non-aromatic compound. Okay, so that's just, in terms of free energy, it's just a very unfavorable thing to do. Okay, but it turns out that we can have substitution reactions with certain electrophiles, okay? Substitution reactions meaning that I used to have a hydrogen here, and then I reacted it with bromine in the presence of iron. We'll see why that's important here. And I've substituted the bromine for the hydrogen. Notice that I've kept my aromaticity. So that's why these substitution reactions are good. There's not going to be any addition reactions. Again, this chapter is going to be the electrophilic aromatic substitution. So all of the other reagents that we're going to be using are electrophiles. And we're going to see that they need catalysts associated with them as well. The bottom line is that in these reactions, we're going to see that the ring itself is playing the role of the nucleophile, but it's not really a great nucleophile. So we're going to need some banging electrophiles in order to make these reactions occur. So one of the hard parts about learning these reactions is not just the sort of combination of reagents that are using, but what's the actual electrophilic species that's involved. First, let's just talk about the reaction mechanism because it's generic to all of these reactions that we're going to see, okay? Again, the ring, and in particular, one of these pi bonds here is going to be playing the role of the nucleophile. So that's what's going to be reaching out and making contact with the electrophile in what we call a nucleophilic attack. Okay, and the identity of this electrophile will be different for each reaction, but this sort of generic reaction scheme is the same, right? The ring is playing the role of the nucleophile, specifically one of the pi bonds in the ring, going to reach out and attack that electrophile. This is going to form what's called a sigma complex, which is basically just a fancy way of saying that you have this carbocation. Get rid of this real quick. You have this carbocation here that's resonance stabilized, right? Because you have all these other conjugated double bonds. You have this positive charge that's going to be stabilized through resonance throughout that ring. Notice that here, this is my carbon that the electrophile is attack. And so now the next step is going to be, I have to get rid of that hydrogen. So that's the last step in these reactions is going to be a proton transfer where there's some base, and the identity of the base is going to be different, for each of the reactions, but there's going to be some base that's going to reach out and accept that proton, allowing that pair of electrons that's in that hydrogen carbon bond to come back down and restore the aromaticity in the ring. Okay, so this is the same generic reaction scheme that we're going to see over and over again in this lecture. The hard part is going to be, what is the identity of this electrophile? And again, it's going to be something that's generated to be like some super duper good electrophile by our catalyst. So these are the different electrophilic aromatic substitution reactions that we're going to see. This lecture actually focuses specifically on these ones. And these ones are left for the next reaction. They got this special name, the Friedel-Crafts reactions. So we're going to focus specifically on these ones first. So again, sort of rewinding in our minds back to when we were learning about alkenes, it was that pi bond that was playing the role of the nucleophile. And then you just had like liquid bromine, where because of the temporary imbalance of electrons, one of those bromine atoms could be more electrophilic. You know, electrons are moving out all the time. So at some moment in time, one of those bromine atoms will be left relatively electron deficient, making it a good electrophile. Okay, that sort of temporary, momentary thing isn't going to cut it with these aromatic or electrophilic aromatic substitution reactions. Specifically, again, the word aromatic, those benzene rings, nice and stable, not a great nucleophile. So we got to use a catalyst to generate a really good electrophile. So this is what iron's going to be doing in this reaction here. So what actually happens, the iron will actually react with a bunch of bromine to create iron 3 bromide. And this is a Lewis acid, meaning that it's relatively electron poor. And so it can actually accept another pair of electrons from the Br2. And that forms this complex here. And this is really our electrophilic species. For these reactions, okay? And the reason why is it's made this terminal bromine here, let me just use the same color, made this terminal bromine here even more electrophilic, because once it sheds this pair of electrons, it actually has this like net positive charge. It's not just going to break off and form some bromine cation that's floating around. This is the electrophilic species here, but you can see that that bromine that's sticking out on the end there is relatively electron deficient. So in our mechanism, again, this is our electrophilic species. Our nucleophile is what? Same for all these reactions. It's going to be that pair of pi electrons, or I like to just generally call it the ring, is playing the role of the nucleophile. And that breaks that bond there. Now we've formed our sigma complex, which is again just a fancy way of saying that we have this resonance stabilized carbocation. Okay. If I was asking you to draw the reaction mechanism, you don't have to draw every single sigma complex, or all three of them rather. If you just gave me one, that's perfectly fine. And then the last step is going to be a proton transfer, where some base is accepting that hydrogen. So actually, let me be clear. That would be these final steps here. You have this base, which is in this case going to be this other bromine. This is important because we got to reform that catalyst, that iron 3 bromide catalyst. So this is going to come down, accept that proton, allowing this pair of electrons to come down and reform our aromatic ring. Okay, so notice, sort of convince yourself by looking back at the other slide. This is the same sort of scheme that we showed before. The difference is that now we have specifically identified the electrophile or the electrophilic species. And this one here is playing, let me just use a different color. And then we have this, which is the identity of our base in this particular reaction. Okay. Okay. And then, just to sort of hammer it home, why is this a substitution reaction that we see instead of an elimination, or I'm sorry, an addition reaction? Again, if it was an addition reaction, we would break our aromaticity, right? So non-aromatic, this is now aromatic, right? So if we had broken that aromaticity, it would be an endergonic reaction, or thermodynamically unfavorable reaction, a non-spontaneous reaction, right? There's a few ways you could say it. This is now indicative of a positive delta G, which is bad. Anyways, it's all about the fact that you're breaking that aromaticity. Another common substrate or catalyst that you can see is aluminum tribromide, literally doing the exact same thing as the iron 3 bromide. And then You can also do this by using aluminum trichloride and chlorine. So then you would have the chlorination product, okay? So we have a way of brominating or forming bromobenzene and a way of forming chlorobenzene. The other halogens, it turns out, don't really work too well. Fluorine's just notorious for having these incredibly violent types of reactions where they release a ton of heat. So, you know, although it might work practically in the lab, it's just unsafe to do, so people don't do it. Iodine, you'll just get terrible yields. It's really slow. So bromine and chlorine are the ones that we can actually use and halogenate this ring. Okay, so notice that if I'm going to use this aluminum trichloride, the sort of structure is almost identical to what we saw with the iron, right, or the iron 3 bromide case. So again, we have this sort of weird complex where our terminal chlorine is left relatively electron deficient. So this is our good electrophile for these particular reactions, right? Again, hard part with these is you're going to have to know that the electrophilic species has been sort of like souped up by the catalyst. Okay, so from there, everything's the same. You have the nucleophile, which is the ring, going and attacking the electrophile. You form your sigma complex or your resonance stabilized carbocation. And then the last step is, again, some base is going to come along and accept that proton, allowing the ring to form back as an aromatic ring. In this case, it's this chlorine so that we can reform our catalyst, the aluminum trichloride. Okay, so now sulfonation, or putting an SO3H group on there. Here, you're going to need to use sulfuric acid, but particularly fuming sulfuric acid or warm concentrated sulfuric acid. The reason why it has to be that fuming sulfuric acid is because our special electrophile is actually going to be this SO3 gas, okay? So in the vapors of sulfuric acid is this SO3. This is our electrophile. You can see in this electron density map that because of those double bonded oxygens and how oxygen is more electronegative, there's also this argument of the p orbitals. Bottom line is that you're left with a relative lack of electron density on that sulfur, meaning that it's a really, really good electrophile. So again, kind of our first, or going back to our generic reaction mechanism here, you have the electrophilic species. You're going to have the nucleophile, which is the ring attacking that electrophile. That again forms your sigma complex. In order to, whoops. Okay, so now we have our sigma complex. We have to get rid of that hydrogen. So some base, in this case, it's going to be water, is going to come along and snatch that hydrogen, allowing this pair of electrons to come down and reform that aromatic ring. There's actually one last step in the sulfonation, which is you're left with this deprotonated oxygen here. So there's going to be another proton transfer that's going to sort of cap that off. Okay. So again, the key here is that you have that SO3, that's your electrophilic species. Sulfur trioxide. This is one of the only electrophilic aromatic substitution reactions that's readily reversible. So by using concentrated hot or fuming sulfuric acid, I can get my sulfonation product. If I use dilute sulfuric acid, I can actually knock that group off, taking me back to just my normal benzene. This is going to be something that's going to be kind of key later on in the chapter, but just make note of that now that we can reverse this reaction. All right, and the last one is a nitration, or putting a nitro group onto our benzene. One of the things I just want to say real quick, about these nitro groups and the sort of like discussions that are in this chapter and built into Canvas, I was very sloppily drawing my nitro groups like this, which is kind of basically it's wrong. It's kind of like a little bit of a shorthand, but it's not correct because if you notice here, the nitrogen has more than 8 electrons in its octet, which isn't allowed. Really, I should have drawn, you know, if you're being really good, you're going to draw these 2 resonance structures for your nitro group. Where you have a formal charge of +1 on your nitrogen and a formal charge of -1 on your oxygen. So again, I was kind of using this sloppy shorthand. I didn't really appreciate it until the end, and there's no way I'm going back and remaking all those figures. But just make note that it really shouldn't be a nitrogen with 10 electrons in its octet. It's kind of a shorthand representation of these 2 resonance structures here. I'll be good about that in the future. I regret that now. But anyways, okay. So now we have a nitration reaction. Notice our reagents, nitric acid and sulfuric acid. Why do you need both of these? Because that's what's going to create your actual electrophilic species, which is the nitronium ion. Which looks like this. Okay, that's the actual electrophilic species in this reaction. How does this create it? This isn't a mechanism that I want you guys to have memorized. You do need to know the electrophilic aromatic substitution mechanism that we've been showing you over and over again. This is just how the nitronium ion is created with the sulfuric acid. Basically, this oxygen gets protonated. Now it becomes a good leaving group and allows us to form the nitronium ion. Okay, but again, the key thing here is that this is the actual active electrophilic species in these reactions. So then what's going to happen? You guys should actually be able to pause and do this reaction mechanism on your own before I go through it, because it just follows the same sort of pattern that we've been doing over and over again, right? What's my nucleophile? The ring, correct. What's the electrophile? In this case, it's this fancy nitronium ion. So that's going to reach out and grab that. What's that going to form? My sigma complex, or my resonance stabilized carbocation. And then the last step is you have some base. In this case, it's water. So notice that in both of these reactions that are catalyzed with these acid, the base is being played by water because these are aqueous solutions. It's going to come and grab that proton, allowing that pair of electrons to come down and reform that aromatic ring. One last reaction that I want to talk about, because it's going to be super duper important in this chapter. It's not an actual electrophilic aromatic substitution reactions. It's actually just how we reduce a nitro group to aniline. And that is by either using iron or zinc in the presence of acid and then following up with NaOH. And notice that that goes from being nitrobenzene to a reduced group here. Do we remember what we call this? One of these benzene derivatives. So we go from being nitrobenzene to aniline, right? Just one of those ones that we should know. This is going to be a really key reaction, because what we're going to see is that these 2 groups play very different roles when they're on these benzene rings. Okay, so this is something that's going to be really important later. It's not an electrophilic aromatic substitution reaction, but still needs to be noted here. Okay, so just to review, these are the reactions that we've gone over in this particular chapter. Again, these are all these electrophilic aromatic substitution reactions, also abbreviated EAS, with the exception of this one down here, which we just want to note is, you know, something that we know how to do now. Again, what we should know about these reactions, obviously the reagents that are needed and the products that are going to be created, but also important is the mechanism and the electrophilic species. So let's just make note of what that is in each of these. When we have these aluminum tribromide or aluminum trichloride, it's the same thing as if you use the iron with the bromine reactions. The active species is going to be something that looks like this. This atom has a positive charge and that aluminum has a negative charge. Okay, you don't have to draw in all your electron dots if you want to go for it, but we do need to be able to draw the structure of the active electrophilic species. So that's this one here. If it's chlorine, it's very similar. Again, remember my charges. Does anybody remember what it was for the sulfonation reactions? That's that sulfur trioxide. Just to draw the structure out. And what about for the nitration reactions? That's that O2 plus or, okay. Yeah, so again, in terms of these reactions, you sort of just need to know not only what the reagents are, but also sort of that active electrophilic species. Yeah, cool.